If we look at the reactant concentration over time for a zeroth order reaction, we get a straight line. The initial reactant concentration is the point at t equals 0 seconds, and the concentration decreases over time since we're dealing with a reactant. The slope of this straight line decrease is -1 times the rate constant. As implied by the rate law, for a zeroth order reaction, the rate does not depend on the reactant concentration. The equation that relates the concentration of a reactant at a specific point in time to the initial concentration, known as the integrated rate law, is a straight line formula. The concentration of the reactant A at any point in time, A sub t, is equal to -k times t, the time, plus the initial concentration of A sub 0. A common example of a situation where a reaction is zero order, or independent of reactant concentration, is when the reaction takes place in contact with a surface that promotes the reaction. Here, the decomposition of ammonia, a zeroth order reaction, takes place on the surface of certain metals or other solids. The ammonia molecules don't decompose until they are in contact with a solid surface. Once they reach the surface and decompose, the decomposed molecules will be replaced by ones from the gas phase, so the amount of molecules on the surface remains constant. This constant rate is what we observe in a zero-order reaction. Fun fact, another zero-order reaction, albeit one that works in a very different way than the one shown here, is the reaction that your body uses whenever you drink alcohol. The rate at which your liver removes alcohol from your bloodstream is also zero-order. In other words, it proceeds at a constant rate until all of the alcohol is cleared. Anyway, while zero-order reactions are not uncommon, most reactions do, in fact, depend on reactant concentrations in various ways, so these reactions will be first-order or higher. For a first-order reaction, one where the rate law is equal to the rate constant multiplied by one reactant's concentration raised to the first power. Through the magic of calculus, we can derive an integrated rate law for these types of reactions as well. That law is shown at the bottom of the screen, where the natural log of the concentration of a reactant at any given point in time, A sub t, is equal to -k times t plus the natural log of the initial concentration of the reactant, A sub 0. Just like a plot of concentration versus time gave a straight line for a zero-order reaction, the integrated rate law here implies that a plot of natural log of concentration versus time will be a straight line for a first-order reaction, and the slope of that line will be -k. This means that if we plot concentration versus time for a first-order reaction, we don't get a straight line, but an exponential decay curve. Instead, if we take the natural log of the reactant concentration and plot that against time, we do get a straight line, and the slope of this line is -k. That decomposition reaction of N2O5 that we saw earlier happens to be a first-order reaction. And sure enough, if we take the data from earlier and plot the natural log of N2O5 concentration versus time, we get a straight line. And by using standard methods using data points on a straight line, we can calculate the slope of this line, which turns out to be -0.0017 inverse seconds. Since this is equal to -k, we can determine that the rate constant for this reaction is k equals positive 0.0017 inverse seconds. For first-order reactions, we can determine what's called the half-life of the reaction, or the amount of time required for the reactant concentration to be cut in half from its present value. If we know the rate constant, we can plug it into this formula derived from the properties of logarithms. The half-life, t sub 1/2, is equal to the natural log of 2 divided by the rate constant k. The natural log of 2 can be approximated as 0.693, so oftentimes we use that value as a simplification in the formula. Because the reactant concentration decays exponentially over time for a first-order reaction, the half-life is independent of reaction concentration. So after one half-life, the reactant concentration is cut in half. Over 2 half-lives, the reactant concentration is 1/4 of its original value. After 3, 1/8, and so on. The last reaction order that we'll consider specifically are second-order reactions. These are reactions for which the rate law is equal to the rate constant multiplied by a reactant concentration squared. Once again, through the magic of calculus, we can derive an integrated rate law to relate initial reactant concentration to the concentration at any given point in time. The formula is 1 over A sub t equals k times t plus 1 over the initial concentration A sub 0. To see this in action, let's consider the decomposition reaction of nitrogen dioxide. Concentration values for NO2 at different points in time are shown in this table, alongside the natural log of each concentration in one column, and 1 over the NO2 concentration in the last column. Plotting NO2 concentration versus time does not produce a straight line, and neither does a plot of natural log of concentration versus time. So from what we've already discussed, we can see that this can't be either a zero or first order reaction. If, however, we plot 1 over concentration versus time, we get a straight line plot implying that this is a second order reaction. The integrated rate law implies that the slope of this line is equal to the rate constant. And if we calculate this slope using 2 points, we get a value for the rate constant of 0.54 per molar per second. Since the y-axis is 1 over concentration, or 1 over molarity, and we divide that by time in seconds, you can probably see where these units come from. It's possible to calculate the half-life for a second-order reaction, but it's different than for a first-order reaction. First of all, the half-life is 1 over the rate constant times the initial concentration. This formula implies, correctly, that the half-life for a second-order reaction increases over time as the reactant concentration goes down. In fact, analysis shows that each successive half-life is twice the length of the preceding one. Let's recap the differences between first and second-order reactions. Each of these, of course, tells us the exponent applied to reactant concentration in the rate law. We saw the integrated rate law for each reaction and how plotting concentration and time varies between each. For a zero-order reaction, the graph of concentration versus time is linear. For first order, the natural log of concentration versus time is linear. And for a second-order reaction, the plot of 1 over concentration versus time is linear. In each case, the graph gives the value of the rate constant, where k is equal to the slope of those straight lines, or the negative of the slope for zero and first-order reactions. And the half-life formulas are shown here as well. Only first-order reactions have a constant half-life. For a zero-order reaction, each successive half-life is shorter than the previous one, while for a second-order reaction, each successive half-life is longer than the previous one. All of them depend on the rate constant, however. Speaking of rate constants, let's talk more about those. Not only does k depend on the particular reaction, but even for the same reaction, k varies with temperature. Perhaps unsurprisingly, the rate of virtually all reactions speeds up as the temperature increases. As an example, the reaction between magnesium metal and water is essentially non-existent in cold water, but much more vigorous in hot water. We can see the increased reactivity in the picture at the right, as evidenced by the formation of bubbles and the pink color of the phenolphthalein indicator in the solution. You can see that hydroxide ions are formed as a product of the reaction, making the solution basic, and hence the phenolphthalein indicator turns pink. While it's not really surprising that heating a reaction makes it go faster, we can still ask what causes this effect. What we see here is known as a reaction progress diagram, or reaction coordinate diagram. The x-axis represents reaction progress over time, and the y-axis shows the potential energy of the system. As a reaction progresses, the kinetic energy of reactant atoms, molecules, or ions is first converted into increased potential energy. This happens until the potential energy reaches a maximum, a point known as the transition state of the reaction. Beyond this point, energy is converted back into kinetic energy as the products are formed. The potential energy difference between the reactants and the transition state, shown here in green, is known as the activation energy. This is the amount of energy the reactants need to overcome to actually convert into the products. The energy difference between the reactants and products, delta E, can also be seen. In this example diagram, the products are lower in potential energy than the reactants, so delta E is negative. This tells us that the reaction shown here must be exothermic. If the products had been higher in energy than the reactants, delta E would be positive and the reaction would be endothermic. How does temperature play into this? To explain, we need to discuss collision theory. This, in a nutshell, states that as the average kinetic energy of the atoms, molecules, or ions in a chemical reaction increases, as it does when the temperature increases, the collision rate between them will increase due to their average increased speed. On this graph, where the x-axis represents collision energy, we can see the point labeled as the activation energy corresponding to the minimum energy needed for a reaction to occur when two molecules collide. The area to the right of this point represents the fraction of molecular collisions with enough energy for this to occur. The purple curve represents the distribution of molecular kinetic energies for a higher temperature sample versus the blue curve representing the same for a low temperature sample. The area to the right of the activation energy is larger for the purple curve, meaning that collisions between the molecules are more likely to cause a reaction when the molecules are higher in temperature. The relationship relating the rate constant to temperature is shown here in the Arrhenius equation. K, of course, is the rate constant. A is the collision frequency factor, EA is the activation energy, R is the gas constant, and T is the temperature. We've seen most of these things in the previous few slides, or in the case of R, a few chapters ago. The collision frequency factor, A, depends on the particular reaction and accounts for the fact that when molecules collide, in order to react, they not only need enough energy, but also must approach each other in the correct orientation in 3D space. We can use the Arrhenius equation to experimentally determine the activation energy for a reaction. By rearranging the equation and plotting the natural log of the rate constant against 1 over temperature, we get a straight line plot. The slope of this plot is negative EA over R. Since R is a constant, 8.314 joules per mole Kelvin, we can find the activation energy, EA. You can imagine that by conducting experiments to vary the reactant concentration and measure the reaction rates, you can determine the reaction order, from there use the rate law to calculate K, and then perform the same set of experiments at different temperatures to find the value of K at each temperature, and plot the results as shown to find the activation energy. And that's actually how activation energy is determined in, say, research laboratories.